Imagine for a moment that time itself could stretch and bend, like a gentle river that flows faster in some places and slower in others. Picture an astronaut floating weightlessly through the cosmos, their body carried along currents of spacetime that move just a little differently than the currents flowing past you and me here on Earth. When they return from their journey among the stars, something remarkable has happened. They have aged ever so slightly less than those they left behind. This isn't science fiction. This is the beautiful, mysterious reality of time dilation, one of the most profound discoveries in all of human understanding. Hi, I'm Luna, and if you love falling asleep to curious science, quiet wonder, and starry night stories, you're in the right place. So grab your coziest blanket, get comfy, and don't forget to hit like and subscribe because tonight, we're going to drift through the gentle currents of time itself, exploring how Einstein's revelations about space and time explain why astronauts return from their missions having experienced time just a little differently than the rest of us. We'll journey through the peaceful mathematics of relativity, float alongside twin paradoxes, and discover how every moment of our lives unfolds within the flexible fabric of spacetime. Time feels so constant, doesn't it? The steady tick of a clock, the rhythm of our heartbeats, the slow turn of day into night. For centuries, humans believed time flowed like a great, unchanging river, the same everywhere, always moving at the same steady pace, whether you were standing still on Earth or racing through space at incredible speeds. This was the world of Isaac Newton, where time was absolute, universal, ticking away identically for every observer in the cosmos. But nestled within this comfortable certainty lay mysteries that would eventually unravel our understanding of time itself. Light, that most ethereal of phenomena, behaved in ways that didn't quite fit the Newtonian picture. Scientists in the late 1800s conducted careful experiments, measuring how light moved through space, expecting to find that light would travel faster or slower, depending on Earth's motion, through what they imagined was a universal medium called the ether. What they found, instead, was deeply puzzling. Light seemed to travel at exactly the same speed, no matter how fast the Earth was moving, no matter which direction they pointed their instruments. It was as if light existed in its own perfect realm, untouched by the motion of planets and stars. This discovery would require a complete reimagining of space and time, and the person who would provide that new vision was a young patent clerk in Switzerland named Albert Einstein. Einstein possessed a rare gift for thinking about the fundamental nature of reality. While others saw light's constant speed as a problem to be solved, Einstein recognized it as a profound clue about the nature of the universe itself. In his quiet moments, perhaps walking along the rivers of Bern or sitting in his small apartment, Einstein began to construct a new picture of reality, one where time itself could bend and flow like water. The key insight came from accepting something that seemed impossible. If light always travels at the same speed for every observer, regardless of how fast they're moving, then something else must be flexible to make this work. That something, Einstein realized, was time itself. Time must stretch and compress, speed up and slow down, to ensure that light speed remains constant for everyone who measures it. This wasn't just a minor adjustment to physics. It was a complete revolution in how we understand the most basic aspects of existence. Space and time, which had seemed separate and absolute, were revealed to be intimately connected, woven together into a single fabric that Einstein called spacetime. This fabric could be bent, stretched, and curved by matter and energy, and these distortions would affect how time flows for different observers. Picture spacetime as a vast, gentle ocean. When you drop a stone into still water, ripples spread outward, creating waves and currents. In spacetime, mass and energy create similar distortions, warping the fabric of reality itself. A massive object like Earth creates a depression in spacetime, like a bowling ball placed on a stretched rubber sheet. These warps in spacetime don't just affect the paths of objects moving through space, they affect the flow of time itself. The mathematics behind this vision is elegantly beautiful, expressed in equations that describe how space curves and time dilates. But beyond the mathematical formalism lies something even more wondrous, the realization that time is not the rigid backdrop against which events unfold, but an active participant in the cosmic dance, flowing faster here and slower there, responding to motion and gravity in ways that would have seemed magical to our ancestors. To understand how time dilation affects astronauts, let's embark on a thought experiment that has captivated physicists and dreamers alike: the twin paradox. Imagine two identical twins, Sarah and Emma, both 25 years old, standing together on a summer evening, watching the first stars appear in the darkening sky. Sarah has just been selected for humanity's first interstellar mission, a journey to a star system 20 light-years away. As they stand there, breathing the warm evening air, neither twin realizes they are about to embark on fundamentally different journeys through time itself. Sarah will travel at tremendous speeds through the cosmos, while Emma will remain on Earth, living her life at the gentle pace our planet provides. When they reunite decades later, they will have aged differently, not because of any medical intervention or life choice, but because of the fundamental nature of time itself. The night before Sarah's departure, the twins spend hours talking, perhaps walking along a quiet beach where waves lap gently against the shore. They make plans for Sarah's return, imagining the stories she'll tell, the wonders she'll have seen. Neither suspects that when Sarah returns, she will have lived through fewer birthdays than her earthbound sister, her body marking the passage of time according to a different rhythm altogether. Sarah's spacecraft accelerates gradually, smoothly, building speed day by day, until it reaches a significant fraction of light speed, perhaps 60% the speed of light. At these tremendous velocities, something beautiful and strange begins to happen. Time aboard Sarah's ship starts to flow more slowly relative to time on Earth. Not that Sarah notices, to her, everything aboard the ship feels perfectly normal. Her heartbeat maintains its regular rhythm, her thoughts flow at their usual pace, and the ship's chronometers tick away seconds just as they always have. But back on Earth, Emma's clocks tick just a little faster than Sarah's. If Emma could somehow peer through a cosmic telescope and watch Sarah moving through her daily routine aboard the speeding ship, she would see Sarah's movements appearing slightly slowed, like a film played at reduced speed. Sarah's morning coffee would seem to cool more slowly. Her books would appear to be read at a leisurely pace, and even Sarah's laughter would seem to ring out in a slightly deeper tone. Meanwhile, from Sarah's perspective aboard the racing ship, something equally strange would be happening. Looking back toward Earth through her own impossibly powerful telescope, Sarah would see Emma's life appearing to unfold in slight fast-forward. Emma's days would seem to pass more quickly. Seasons would cycle with increased speed, and Emma herself would appear to age at an accelerated rate compared to Sarah's own experience of time. This reciprocal effect continues throughout Sarah's journey to the distant star system. Years pass aboard the ship, marked by the gentle routine of space travel, watching the cosmic landscape slowly change, tending to the ship's systems, perhaps growing plants in the ship's garden under artificial suns. Sarah experiences every moment fully, unaware that each of her heartbeats, each of her thoughts, each page she turns is happening within a time stream that flows just slightly more slowly than the one carrying her sister through her life on Earth. The mathematics underlying this temporal difference are precise and predictable. At 60% the speed of light, time dilation factors become significant, but not extreme. For every year that passes aboard Sarah's ship, about 1.25 years pass on Earth. The difference accumulates slowly, like interest in a cosmic bank account, growing larger as the journey progresses. When Sarah reaches the distant star system, she spends time exploring, perhaps landing on alien worlds where no human foot has ever stepped. She watches foreign sunrises paint alien skies in colors that have no names, breathes air that has never filled human lungs, and makes discoveries that expand human knowledge in ways that would have been impossible without her journey. All of this exploration takes place within her slowed time stream, each moment of wonder unfolding at the gentle pace dictated by her tremendous speed through space. For the return journey, Sarah's ship must decelerate, turn around, and accelerate back toward Earth. During these periods of acceleration and deceleration, additional relativistic effects come into play. But the fundamental principle remains the same: high speed means slower time. As Sarah races back toward Earth, more years accumulate on both timelines, with Earth's clocks continuing to tick slightly faster than those aboard the ship. When Sarah's ship finally enters Earth's solar system decades later, the reunion of the twins reveals the profound reality of time dilation. Sarah emerges from her ship having experienced, let's say, 32 years of life since her departure. She has celebrated 32 birthdays, lived through 32 full cycles of seasons, artificial though they may have been aboard her ship, and aged 32 years in every biological sense. Emma, waiting on Earth to greet her returning sister, has experienced 40 years of life. She has seen 40 springs arrive, has celebrated 40 birthdays, and carries in her face and body the gentle marks of 4 decades of Earth time. The twins, once identical, now show the unmistakable signs of having lived through different amounts of time. Sarah appears 8 years younger than Emma, not because of any technology or medical intervention, but because she has literally experienced less time. This age difference isn't merely theoretical or mathematical. It represents a real difference in how much life each twin has lived. Sarah has had fewer moments to think, fewer sunrises to witness, fewer books to read. Her biological processes have run for less total time. Her cells have divided fewer times, and her body has accumulated less wear from the simple passage of years. She has, in the most literal sense possible, aged less than her earthbound twin. The reunion is both joyful and poignant. The twins embrace, their joy at being reunited tinged with the strange reality that they have become living proof of relativity theory. Sarah's stories from distant stars are told by a face that carries 8 fewer years of life, while Emma listens with eyes that have seen 8 additional years of Earth's changing seasons. The beautiful reality of time dilation emerges from one of the most fundamental principles in all of physics: the idea that the speed of light in vacuum is constant for all observers, regardless of their motion. This principle, seemingly simple, leads to consequences so profound they revolutionized our understanding of reality itself. Let's imagine light as nature's perfect metronome, keeping time for the entire universe. Unlike sound, which travels faster or slower depending on wind conditions and temperature, light maintains its cosmic speed limit with unwavering precision. Whether you're standing still on Earth or racing through space at tremendous velocities, light passes you at exactly the same speed, approximately 300 million meters per second. This constancy of light speed creates a beautiful puzzle. Imagine you're standing on a train platform as a high-speed train approaches. If someone on the train throws a baseball forward, you would naturally expect the baseball's speed relative to you to be the train's speed plus the baseball's throwing speed. This addition of velocities is what we experience in our everyday world, where speeds are much smaller than light's cosmic velocity. But light doesn't behave this way. If someone on that same train shines a flashlight forward, the light doesn't travel at the train's speed plus light speed. It travels at exactly light speed, the same speed you would measure if the train were standing still. This seemingly impossible behavior is what led Einstein to his revolutionary insights about space and time. For light to maintain constant speed regardless of the observer's motion, something else must be flexible. Einstein realized that space and time themselves must stretch and compress to accommodate light's unwavering pace. When you move very fast relative to another observer, your measurements of space and time adjust in precisely the right way to ensure that you both measure the same speed for light. The mathematical relationship governing time dilation is elegantly simple. The factor by which time slows is determined by what physicists call the Lorentz factor, represented by the Greek letter gamma. This factor depends only on velocity. The faster you move, the more dramatically time dilates. At everyday speeds, gamma is so close to 1 that time dilation is completely negligible. But as speeds approach the speed of light, gamma grows larger, and time dilation becomes increasingly significant. The formula reveals something profound about the nature of reality. Time dilation isn't a side effect or correction to some more fundamental truth. It is a fundamental feature of how time works. Time doesn't flow at a universal rate because there is no universal reference frame from which to measure such a rate. Instead, time flows at whatever rate is necessary to preserve the constancy of light speed for all observers. This principle extends beyond just fast-moving spacecraft. Any form of motion, no matter how small, creates time dilation. When you walk across a room, time flows slightly more slowly for you than for someone sitting still. Though the effect is so tiny, it's utterly unmeasurable with any conceivable technology. The GPS satellites orbiting Earth experience measurable time dilation due to their orbital velocities, and this effect must be corrected for the system to provide accurate positioning. The beauty of time dilation lies not just in its mathematical elegance, but in its deep connection to the structure of spacetime itself. Einstein showed that space and time are not separate entities, but different aspects of a single four-dimensional fabric. Motion through space affects the flow of time because space and time are intimately connected. When you move rapidly through space, you're also changing your path through the time dimension of spacetime. Think of spacetime as a vast landscape with hills and valleys, where the topology is shaped by matter and energy. Your path through this landscape determines how you experience time. Different paths, corresponding to different velocities, lead to different experiences of time's passage. There's no single correct way to move through spacetime, no preferred reference frame that experiences true time. Each observer's experience of time is equally valid, equally real. This insight extends to acceleration as well. When Sarah's spacecraft speeds up or slows down during her interstellar journey, additional time dilation effects come into play. During periods of acceleration, the situation becomes more complex, resembling the effects of gravity on time's flow. The astronaut experiences what feels like artificial gravity due to the acceleration, and this gravitational effect also influences the passage of time. The connection between acceleration and gravity runs even deeper than initially apparent. Einstein realized that acceleration and gravity are fundamentally equivalent, a principle he called the equivalence principle. Someone in a windowless room cannot tell whether they're experiencing gravity from a massive object below or acceleration from rockets pushing the room upward. This equivalence means that gravity also affects time's flow, leading to gravitational time dilation. On Earth's surface, Time flows slightly more slowly than it does in the vacuum of space, far from any massive objects. This gravitational time dilation is tiny, but measurable clocks run about 22 microseconds per year slower at sea level than they would in the absence of Earth's gravity. For astronauts orbiting Earth, this gravitational effect partially cancels the velocity-based time dilation from their orbital motion, creating a complex interplay between different relativistic effects. The International Space Station provides a perfect laboratory for observing these competing effects. The station orbits at about 400 kilometers above Earth's surface, moving at roughly 28,000 kilometers per hour. At this speed, velocity-based time dilation causes clocks aboard the station to run slow by about 7 microseconds per day. However, because the station is farther from Earth's center than surface-bound clocks, it experiences weaker gravity, causing gravitational time dilation to speed up the station's clocks by about 45 microseconds per day. The net effect is that time aboard the International Space Station flows about 38 microseconds per day faster than time on Earth's surface. This means that astronauts on long-duration missions actually age slightly faster than people on Earth, not slower as pure velocity-based time dilation would suggest. The gravitational effect dominates because the station's orbital altitude reduces gravitational time dilation more than the station's orbital speed increases velocity-based time dilation. For astronauts traveling to more distant destinations at much higher speeds, velocity-based time dilation would dominate, causing them to age more slowly than Earth-bound humans. The faster the journey, the more pronounced this effect becomes. At 90% the speed of light, time dilation becomes dramatic. Every year experienced by the astronaut corresponds to about 2.3 years on Earth. These effects aren't just theoretical curiosities. They're measurable realities that influence everything from satellite navigation to particle physics experiments. Every GPS satellite carries atomic clocks that must account for both velocity-based and gravitational time dilation to maintain the system's accuracy. Without these corrections, GPS positioning would drift by several kilometers per day, rendering the system useless for navigation. In particle accelerators, scientists routinely observe time dilation as subatomic particles race around collision rings at speeds approaching that of light. Particles that would normally decay in microseconds live much longer when moving at relativistic speeds. Their internal clocks, slowed by the same time dilation, effects that would influence human astronauts at similar velocities. While the time dilation experienced by fast-moving astronauts captures our imagination, there's another form of time dilation that surrounds us every moment of every day: the gentle warping of time by gravity itself. This gravitational time dilation is perhaps even more remarkable than its velocity-based cousin, revealing that massive objects don't just bend space, but also stretch and compress the flow of time. Picture Earth not just as a solid sphere of rock and metal, but as a cosmic presence that creates ripples in the fabric of spacetime itself. Just as a heavy stone placed on a stretched rubber sheet creates a depression that affects the movement of marbles rolled nearby, Earth's mass creates a gravitational well that influences how time flows for everything within its influence. The deeper you are in this gravitational well, the closer you are to Earth's center, the more slowly time flows relative to regions of weaker gravity. This means that time passes slightly more slowly at sea level than it does on a mountaintop, slightly more slowly in your basement than in your attic, and dramatically more slowly near the surface of incredibly dense objects like neutron stars or black holes. This gravitational influence on time emerges from the same fundamental insights that led Einstein to understand velocity-based time dilation. The equivalence principle, the idea that acceleration and gravity are indistinguishable, means that sitting in Earth's gravitational field is equivalent to being in a constantly accelerating reference frame. And just as acceleration affects time's flow, so does gravity. To understand how this works, imagine yourself in an elevator far out in space, with no gravitational fields nearby. If the elevator begins accelerating upward at exactly the same rate as Earth's gravitational acceleration, about 9.8 meters per second squared, everything inside the elevator would behave exactly as if you were sitting in a stationary elevator on Earth's surface. Objects would fall toward the floor at the same rate. You would feel pressed against the floor with the same force, and pendulum clocks would tick at the same rate. But something subtle and profound happens to light signals in this accelerating elevator. If someone outside the elevator shines a laser beam horizontally across the elevator's path, someone inside the accelerating elevator would see that beam curve downward, appearing to fall just like any material object. From the perspective of someone inside the elevator, gravity seems to bend light. More remarkably, if someone at the bottom of the elevator shines a light toward someone at the top, the acceleration of the elevator causes the light to appear shifted toward higher frequencies, what physicists call a blue shift. Conversely, light shown from top to bottom appears redshifted, its frequency decreased. Since acceleration and gravity are equivalent, the same frequency shifts must occur in actual gravitational fields. These frequency shifts reveal something profound about time in gravitational fields. The frequency of light is intimately connected to the rate at which time flows for the observer who emitted that light. When light climbing out of a gravitational well becomes redshifted, it's revealing that time flows more slowly deeper in the gravitational well. The deeper the well, the more pronounced the effect. This gravitational time dilation has been measured with extraordinary precision using atomic clocks. In 1971, physicists Haefel and Keating flew atomic clocks around the world on commercial airliners, comparing their readings to reference clocks that remained stationary. The flying clocks, experiencing both the velocity-based time dilation from their motion and the reduced gravitational time dilation from their altitude, showed exactly the time differences predicted by Einstein's theories. More recently, scientists have measured gravitational time dilation over much smaller distances. In 2010, researchers at the National Institute of Standards and Technology detected gravitational time dilation between atomic clocks separated by only 33 centimeters of height, a remarkable demonstration of how precisely we can now measure time's flow in different gravitational conditions. For astronauts, gravitational time dilation creates effects that vary depending on their mission profile. Astronauts aboard the International Space Station experience weaker gravity than people on Earth's surface because they're farther from Earth's center. This reduced gravitational influence causes their clocks to run slightly faster than Earth-based clocks, an effect that actually dominates over the velocity-based time dilation from their orbital motion. But for astronauts traveling to other celestial bodies, gravitational time dilation can work in different ways. On the Moon's surface, where gravity is about 1/6 as strong as Earth's, time flows slightly faster than it does on Earth. An astronaut spending a year on the Moon would age about 56 microseconds more than someone spending that same year on Earth. A tiny effect, but a real one. The most dramatic gravitational time dilation effects occur near extremely massive and dense objects. Near a neutron star, where gravity can be billions of times stronger than Earth's, time dilation becomes severe. An astronaut unfortunate enough to approach such an object would find their time flowing much more slowly relative to distant observers, though they themselves would experience time normally. Black holes represent the ultimate extreme of gravitational time dilation. Near a black hole's event horizon, gravity becomes so strong that time dilation approaches infinity. An astronaut falling toward a black hole would appear to outside observers to slow down dramatically as they approached the event horizon, their image red-shifting and fading, as time dilation stretched each moment of their experience into longer and longer intervals, as seen from far away. But perhaps the most beautiful aspect of gravitational time dilation is how it reveals the deep connection between matter, space, and time. Massive objects don't just attract other objects through some mysterious force acting at a distance. They actually reshape the geometry of spacetime itself. Time flows differently near massive objects because the presence of matter and energy changes the very structure of the temporal dimension. This reshaping of spacetime is what we experience as gravity. When you drop a ball, it's not being pulled by some invisible force. It's following the straightest possible path through curved spacetime. The ball's trajectory through space and time has been altered by Earth's mass, creating what we perceive as gravitational attraction, but which is actually the ball following spacetime's natural geometry. The same curvature of spacetime that deflects the ball's path also affects time's flow. Space and time are so intimately connected that you cannot curve one without affecting the other. When mass curves space, it simultaneously stretches and compresses time, creating the gravitational time dilation that influences every ticking clock, every beating heart, every moment of experience for every conscious being in the universe. This intimate connection between matter and time suggests profound questions about the nature of existence itself. If time's flow depends on the distribution of mass and energy in the universe, then time itself has evolved as the universe has evolved. In the early universe, when matter was distributed more uniformly, the gravitational effects on time would have been different than they are today, with its galaxies, stars, and planets creating complex patterns of time dilation across the cosmos. The effects of time dilation extend far beyond the dramatic scenarios of interstellar travel or extreme gravitational environments. These relativistic effects subtly influence every aspect of our technological civilization, requiring constant corrections and adjustments to maintain the precision our modern world demands. Perhaps nowhere is this more evident than in the global positioning system, where satellites orbiting Earth must account for both velocity-based and gravitational time dilation to provide accurate location information. GPS satellites orbit at altitudes of about 20,000 kilometers, where they experience both weaker gravity than objects on Earth's surface and significant orbital velocities of roughly 14,000 kilometers per hour. The interplay between these two effects creates a complex pattern of time dilation that engineers must carefully calculate and correct. The reduced gravity at orbital altitude causes the satellite's clocks to run about 45 microseconds per day faster than identical clocks on Earth's surface. Meanwhile, their orbital velocity creates velocity-based time dilation that slows their clocks by about 7 microseconds per day. The net effect is that satellite clocks run approximately 38 microseconds per day fast compared to Earth-based reference clocks. This might seem like a tiny discrepancy, but GPS relies on incredibly precise timing to determine positions. The system works by measuring the time it takes radio signals to travel from satellites to receivers on Earth. Since radio waves travel at the speed of light, even microsecond errors in timing translate to positioning errors of hundreds of meters. Without corrections for relativistic time dilation, GPS would be virtually useless for navigation, accumulating errors of several kilometers per day. To maintain accuracy, GPS satellites carry atomic clocks that are pre-adjusted to run slightly slow while on Earth, so they'll keep correct time once in orbit. Additionally, the system continuously monitors and corrects for relativistic effects, ensuring that the timing signals remain synchronized with Earth-based reference standards. This makes GPS one of the most widespread practical applications of Einstein's relativity theories, quietly functioning in millions of devices around the world. But the influence of time dilation extends beyond navigation systems. In particle physics research, scientists regularly observe relativistic effects in high-energy experiments. When particles are accelerated to speeds approaching that of light, their behavior changes in precisely the ways predicted by relativity theory. Unstable particles that would normally decay in microseconds live much longer when moving at relativistic speeds, their internal clocks slowed by time dilation. These observations provide continuous confirmation of relativity theory's predictions. Every day, in laboratories around the world, particles are accelerated to tremendous speeds, and every day they behave exactly as Einstein's equations predict they should. The Large Hadron Collider at CERN regularly accelerates protons to 100% the speed of light, creating time dilation factors of over 7,000. At these speeds, particles experience time so slowly that they can complete thousands of trips around the 27-kilometer ring before their relativistic clocks advance by a single microsecond. The practical applications of understanding time dilation continue to expand as our technology becomes more sophisticated. Precision timing is crucial for telecommunications networks, financial trading systems, and scientific research facilities. As these systems demand ever greater accuracy, relativistic effects that were once negligible academic curiosities become important practical considerations. Even everyday technologies are beginning to feel the influence of relativistic effects. Modern computer processors operate at speeds where electromagnetic signals take measurable time to travel between components. While current processors don't require relativistic corrections, the continuing push toward faster computational speeds may eventually require engineers to consider time dilation effects in circuit design. The biological implications of time dilation, while most dramatically illustrated in science fiction scenarios, have real consequences for long-duration space missions. Astronauts on the International Space Station experience a complex mixture of effects from reduced gravity, radiation exposure, and subtle time dilation. While the time dilation effects are far too small to noticeably influence aging, they represent part of the unique environment that space travelers experience. As human civilization contemplates missions to Mars and other distant destinations, time dilation will become a more significant factor. A round trip to Mars would involve months of travel at speeds much higher than current spacecraft achieve, potentially creating measurable time dilation effects. While these effects would still be tiny compared to the duration of the mission, they represent the beginning of humanity's direct experience with relativistic travel. The psychological and philosophical implications of time dilation become more profound as we consider longer journeys to more distant destinations. An astronaut traveling to nearby star systems would return to find Earth changed in ways they couldn't have predicted before departure. The society that sent them on their mission might have evolved technologically and culturally in ways that make the astronaut a visitor from the past, carrying perspectives and knowledge that Earth has moved beyond. This temporal displacement creates unique challenges for interstellar exploration. Unlike the geographic exploration of Earth's surface, where explorers could expect to return to essentially the same civilization that sent them forth, interstellar travelers must accept that their journey through space is also a journey through time, potentially carrying them into futures they cannot anticipate. Yet there's something beautiful about this aspect of time dilation, the way it connects space travel to time travel, making every journey into the cosmos also a journey into tomorrow. The astronaut racing toward distant stars doesn't just cross space. They slide gently forward through time, experiencing less of the universe's aging, while Earth continues its steady progression through the years. This sliding through time isn't just a side effect of space travel. It's a fundamental aspect of how motion through spacetime works. Every step you take, every movement you make, every moment of your life involves travel through both space and time. The faster you move through space, the slower you move through time, creating a conservation principle where your total motion through spacetime remains constant. The quantum dance of time at the smallest scales of reality, where quantum mechanics governs the behavior of atoms and subatomic particles, time dilation reveals new layers of complexity and wonder. The intersection of relativity and quantum mechanics creates a realm where time's flow becomes even more nuanced, influenced not just by velocity and gravity, but by the strange probabilistic nature of quantum reality itself. In the quantum world, particles exist in superpositions of multiple states simultaneously, collapsing into definite configurations only when observed or measured. This quantum uncertainty extends to the measurement of time itself. When dealing with individual particles moving at relativistic speeds, the precise moment of any event becomes subject to quantum uncertainty, creating a fuzzy boundary between cause and effect that challenges our classical understanding of temporal order. Consider a high-energy particle racing through space at nearly the speed of light. In the classical picture, we might imagine tracking this particle's position and velocity with perfect precision, calculating exactly when it will arrive at any given destination. But quantum mechanics tells us that perfect knowledge of both position and momentum is impossible due to Heisenberg's uncertainty principle. This quantum fuzziness affects not just where the particle is, but when it experiences various events along its journey. The quantum nature of matter also influences how we understand the biological aspects of time dilation. The chemical reactions that power our cells, the neural processes that create consciousness, and the molecular machinery that repairs DNA damage all operate according to quantum mechanical principles. When these processes occur within a time-dilated reference frame, they continue to function normally from the perspective of the observer experiencing that frame. But their relationship to external time becomes more complex. DNA replication, for instance, proceeds through a series of quantum mechanical processes involving the breaking and forming of chemical bonds. An astronaut traveling at relativistic speeds would experience these biological processes at their normal rate, but the accumulation of radiation damage might occur according to a different temporal rhythm. Cosmic ray interactions with biological tissue involve high-energy particles that themselves experience relativistic effects, creating a complex interplay between quantum processes and time dilation. The quantum vacuum itself, the seemingly empty space between particles, bubbles with virtual particle pairs constantly appearing and disappearing. These quantum fluctuations occur on timescales so brief they're barely meaningful in classical terms. Yet they contribute to measurable effects, like the Casimir force between closely spaced metal plates. In regions of curved spacetime, or within rapidly moving reference frames. These quantum vacuum fluctuations experience time dilation, just like any other physical process. This quantum aspect of time dilation becomes especially intriguing when we consider consciousness itself. The neural processes that give rise to thought and experience operate through electrochemical signals involving quantum mechanical interactions between atoms and molecules, while consciousness doesn't appear to depend on quantum coherence effects in any dramatic way. The molecular processes underlying neural activity are fundamentally quantum mechanical in nature. An astronaut's consciousness, therefore, experiences time dilation at the deepest level. Every thought, every memory formation, every moment of awareness unfolds within a time stream that flows differently than the one containing earthbound consciousness. The astronaut's subjective experience of time remains normal. Thoughts flow at their usual pace, memories form at their typical rate, and consciousness maintains its familiar rhythm. But these mental processes are occurring within a temporal framework that has been shifted relative to the rest of humanity. This creates a fascinating philosophical question about the nature of subjective time versus objective time. From the astronaut's perspective, their experience of time is completely normal and represents the true flow of time for their reference frame. From Earth's perspective, the astronaut's mental processes appear slowed, their thoughts unfolding at a leisurely pace that matches their dilated time stream. Neither perspective is more correct than the other. They represent equally valid ways of experiencing the passage of time. The quantum mechanical nature of atomic clocks adds another layer of precision to time dilation measurements. These incredibly accurate timepieces rely on the quantum mechanical energy levels of atoms, counting the oscillations of electromagnetic radiation emitted when electrons transition between precisely defined energy states. The frequency of these atomic transitions provides a natural standard for measuring time that's based on fundamental physical constants. When atomic clocks experience time dilation, the quantum mechanical processes within the atoms continue to operate at their normal rates from the perspective of the clock itself. The electrons still transition between energy levels at their characteristic frequencies, and the clock mechanism still counts these transitions accurately. But the relationship between these quantum oscillations and external time has changed due to the relativistic effects of motion or gravity. This quantum foundation of timekeeping reveals something profound about the nature of time itself. Time isn't just an abstract mathematical parameter. It's intimately connected to the quantum mechanical processes that govern all matter and energy in the universe. When we measure time dilation, we're really observing how the quantum mechanical oscillations that define our time standards are affected by motion through spacetime. The precision of modern atomic clocks has reached extraordinary levels, with the most accurate devices gaining or losing less than 1 second over the entire age of the universe. This incredible precision allows scientists to detect gravitational time dilation over height differences of mere centimeters, and to measure velocity-based time dilation for objects moving at relatively modest speeds. These measurements continue to confirm Einstein's predictions with remarkable accuracy. As our understanding of quantum mechanics and relativity continues to deepen, new phenomena continue to emerge at their intersection. Quantum field theory, which combines quantum mechanics with special relativity, predicts exotic effects like particle creation in accelerating reference frames and the relationship between black hole horizons and quantum entanglement. These cutting-edge areas of physics suggest that time dilation is connected to even more fundamental aspects of reality than we currently understand. The search for a quantum theory of gravity a framework that would fully unify quantum mechanics with general relativity, remains one of physics' greatest challenges. Such a theory would necessarily provide new insights into the quantum nature of spacetime itself, potentially revealing that time dilation emerges from even more fundamental quantum processes operating at the smallest scales of space and time. Time dilation in the cosmic dance. The universe itself provides the grandest stage for observing time dilation effects, where massive celestial objects create complex patterns of curved spacetime that influence the flow of time across cosmic distances. From the gentle time dilation near ordinary stars to the extreme temporal distortions around black holes, the cosmos reveals time's malleability on scales that dwarf human experience. Consider our own sun, that familiar golden disk that rises each morning and sets each evening. While we think of it as a constant, reliable presence, the sun's mass creates a gravitational well that influences time's flow throughout the entire solar system. Time passes slightly more slowly at the sun's surface than it does here on Earth, and more slowly on Earth than it does in the empty space between planets. These differences are tiny by everyday standards, but become significant when we consider the vast timescales over which the universe operates. A clock placed on the sun's surface would fall behind an identical clock in empty space by about 212 seconds per year, a little over 3 minutes annually. Over the sun's lifetime of billions of years, this difference accumulates to thousands of years of temporal displacement. This solar time dilation has subtle but real effects on the planets orbiting within the sun's gravitational influence. Mercury, closest to the sun, experiences the strongest gravitational time dilation in our solar system. Time flows about 0% more slowly on Mercury's surface than it does on Earth, a difference so small it would be imperceptible to any conceivable biological process, yet large enough to be measured by atomic clocks if we were to place them there. The orbital mechanics of the solar system itself provide evidence for relativistic effects. Mercury's orbit precesses. Its elliptical path slowly rotates around the sun at a rate that cannot be fully explained by Newtonian gravity alone. The additional precession, about 43 arcseconds per century, matches exactly the prediction of Einstein's general relativity, arising from the curvature of spacetime near the sun. As we expand our view beyond the solar system, time dilation effects become more dramatic. Neutron stars, the incredibly dense remnants of massive stars that have undergone gravitational collapse, create gravitational fields so intense that time dilation becomes severe. A typical neutron star contains more mass than the sun compressed into a sphere, only about 20 kilometers in diameter, creating surface gravity billions of times stronger than Earth's. Near a neutron star surface, time flows dramatically more slowly than in the surrounding space. An astronaut unfortunate enough to visit such an object would find that every second of their experience corresponds to many seconds as measured by distant observers. If they could somehow survive the intense radiation and gravitational forces and spend an hour on the neutron star's surface, they would return to find that several hours had passed for observers watching from a safe distance. The most extreme time dilation effects in the universe occur near black holes, those mysterious objects where gravity becomes so strong that not even light can escape. Near a black hole's event horizon, the boundary beyond which nothing can return time dilation approaches infinity. An object falling toward the event horizon would appear to outside observers to slow down dramatically, its image redshifting and fading as time dilation stretches each moment into longer and longer intervals. This creates the strange phenomenon known as gravitational time dilation freezing. To an outside observer, nothing ever appears to cross a black hole's event horizon. Instead, infalling objects seem to slow down and freeze at the boundary, their images becoming increasingly redshifted and dim until they fade from view. Yet, from the perspective of the falling object, their journey to the event horizon and beyond proceeds normally, experiencing no unusual slowing of time. This dual perspective reveals something profound about the nature of spacetime near extreme gravitational fields. There is no single, universal way to describe what happens near a black hole. The experience depends entirely on the observer's reference frame. Both the outside observer and the infalling observer experience time normally within their own reference frames, yet they witness completely different versions of events. Stellar mass, black holes, formed from the gravitational collapse of massive stars, typically have event horizons only a few kilometers in radius, but supermassive black holes, found at the centers of galaxies, can have event horizons larger than the orbit of Neptune. These cosmic giants contain millions or billions of times the mass of the Sun, creating gravitational fields that influence time's flow across vast regions of space. The supermassive black hole at the center of our own Milky Way galaxy, known as Sagittarius A, demonstrates these effects on astronomical scales. Stars orbiting close to this 4 million solar mass black hole experience significant gravitational time dilation. The star designated STWO, which follows a highly elliptical orbit, bringing it within about 120 astronomical units of the black hole, experiences time dilation that varies dramatically throughout its 16-year orbital period. When STWO approaches closest to Sagittarius A, it reaches speeds of about 7650 kilometers per second, roughly 2.5% the speed of light, while simultaneously experiencing intense gravitational time dilation. The combination of these effects causes the star's clocks to run slow relative to Earth-based observers, providing astronomers with a natural laboratory for testing relativistic effects in extreme gravitational environments. Recent observations of STWO's orbit have confirmed Einstein's predictions with remarkable precision, detecting both the gravitational redshift of light climbing out of the black hole's gravitational well and the relativistic precession of the star's orbit. These measurements represent some of the most stringent tests of general relativity ever conducted, confirming the theory's predictions in gravitational fields far stronger than anything accessible in terrestrial laboratories. The influence of black holes on time extends far beyond their immediate vicinity. The rotation of massive black holes drags spacetime itself around with them, creating a phenomenon called frame dragging or the lens-thirring effect. Within this dragged region, called the ergosphere, spacetime itself rotates, and anything within this region must rotate along with it, regardless of any effort to remain stationary. This frame-dragging effect creates additional complications for time measurements near rotating black holes. The dragging of spacetime affects not just the spatial coordinates of objects in the vicinity, but also their temporal coordinates, creating complex patterns of time dilation that depend on both distance from the black hole and position relative to its rotation axis. Binary black hole systems, where two black holes orbit each other in an ever-tightening spiral, create some of the most complex spacetime geometries in the universe. As these massive objects dance around each other, they create ripples in spacetime itself, gravitational waves that carry energy away from the system, causing the black holes to spiral inward ever faster. During the final moments before two black holes merge, they can orbit each other hundreds of times per second, creating rapidly changing gravitational fields that cause time dilation to fluctuate dramatically in the surrounding region. The gravitational waves themselves carry information about these extreme time dilation effects, allowing astronomers to study the behavior of spacetime in conditions that would be impossible to recreate in any laboratory. The detection of gravitational waves by facilities like LIGO and Virgo has opened a new window into these extreme environments, providing direct evidence for the most dramatic manifestations of time dilation in the universe. Each gravitational wave detection tells a story of cosmic violence, where black holes or neutron stars merge in cataclysmic events that briefly outshine entire galaxies, all while creating spacetime distortions that influence time's flow across millions of light years. On even larger scales, the expansion of the universe itself creates cosmological time dilation effects. Light from distant galaxies is redshifted not just by their motion away from us, but by the expansion of space itself during the billions of years the light has traveled to reach us. This cosmological redshift reveals that time itself flows differently when viewed across cosmic distances and cosmic time. The most distant galaxies we observe appear to us as they were when the universe was young, their light stretched by billions of years of cosmic expansion. The processes we observe in these ancient galaxies, star formation, stellar evolution, supernova explosions, all appear to unfold in slow motion due to cosmological time dilation, their timescales stretched by the same factor as their light has been redshifted. This cosmological perspective reveals that time dilation isn't just a local phenomenon affecting individual observers or spacecraft. It's a fundamental aspect of how the universe itself evolves and changes. Every photon of light carries within its frequency a record of the time dilation it has experienced during its journey across space and time, telling the story of the universe's expansion and evolution. As we contemplate the vastness of cosmic time dilation effects, from the gentle influence of our sun to the extreme distortions near black holes, we begin to appreciate how profoundly Einstein's insights have changed our understanding of time itself. Time isn't a universal constant, ticking away identically throughout the cosmos. It's a dynamic, malleable aspect of reality that responds to the presence of matter and energy, creating a rich tapestry of temporal experiences across the universe. The measurement and management of time dilation effects has driven the development of some of humanity's most precise technologies, pushing the boundaries of what's possible in terms of accurate timekeeping and navigation. These technological achievements not only enable practical applications like GPS, but also provide the tools necessary for testing the fundamental principles of relativity theory with extraordinary precision. At the heart of modern precision timekeeping lie atomic clocks, devices that harness the quantum mechanical properties of atoms to create time standards of unprecedented accuracy. These remarkable instruments work by counting the oscillations of electromagnetic radiation emitted when electrons transition between precisely defined energy levels within atoms. The frequency of these transitions is determined by fundamental physical constants, making atomic clocks incredibly stable and reproducible. The most accurate atomic clocks currently in existence are based on optical transitions in atoms like strontium or ytterbium, trapped and cooled to temperatures just billionths of a degree above absolute zero. These optical atomic clocks are so precise that they would neither gain nor lose a second over the entire age of the universe, a level of accuracy that borders on the philosophical, representing time measurement so precise it approaches the fundamental limits imposed by quantum mechanics itself. This extraordinary precision allows scientists to detect gravitational time dilation over height differences measured in centimeters. In groundbreaking experiments, researchers have demonstrated that atomic clocks separated by less than a meter show measurable differences in their tick rates due to Earth's gravitational field. These measurements confirm Einstein's predictions at a level of precision that would have seemed impossibly refined just decades ago. The practical challenges of maintaining such precise timekeeping in the presence of relativistic effects require sophisticated engineering solutions. GPS satellites, for instance, carry multiple atomic clocks and sophisticated computer systems that continuously monitor and correct for both velocity-based and gravitational time dilation. The satellites communicate regularly with ground stations, allowing the system to detect and compensate for any timing discrepancies that might arise. The GPS system demonstrates how deeply embedded relativistic corrections have become in our technological infrastructure. Every smartphone that displays your location, every navigation system that guides you to your destination, and every precision timing application that relies on GPS signals depends on calculations that account for Einstein's relativistic effects. Without these corrections, the entire system would be useless for navigation within a matter of days. Beyond navigation, precision timing has become crucial for telecommunications networks that carry internet traffic, phone calls, and data around the world. These networks rely on synchronized timing to route information efficiently and prevent data from arriving out of order or being lost entirely. As data transmission speeds continue to increase, the timing requirements become ever more stringent, potentially requiring relativistic corrections, even for terrestrial networks. Financial markets represent another domain where precision timing has become critical. High-frequency trading systems execute thousands of transactions per second, and the ability to complete trades microseconds faster than competitors can translate to significant financial advantages. These systems require precise time synchronization across multiple locations. And as trading speeds continue to increase, relativistic effects may eventually become relevant even for transactions conducted entirely on Earth. The development of next-generation atomic clocks promises even greater precision and new applications for time dilation research. Nuclear clocks, based on transitions in atomic nuclei rather than electrons, could potentially achieve accuracies thousands of times better than current optical atomic clocks. Such devices would be sensitive enough to detect gravitational time dilation, effects from objects as small as mountains or even large buildings. Portable atomic clocks are also becoming more practical, allowing scientists to conduct time dilation experiments in a wider variety of locations and conditions. These transportable devices could enable measurements of gravitational time dilation in different geographic locations, providing new ways to study Earth's gravitational field and potentially detect underground mass distributions or geological features. The quantum nature of atomic timekeeping creates interesting connections between time dilation and other areas of quantum physics. Quantum entanglement, the phenomenon where particles become correlated in ways that transcend classical physics, might potentially be used to create distributed timing networks that maintain synchronization across vast distances. Such quantum timing networks could provide new ways to study and compensate for relativistic effects. Ion trap atomic clocks, where individual ions are confined using electromagnetic fields and cooled to near absolute zero, represent another frontier in precision timekeeping. These devices can achieve extraordinary stability by isolating single atoms from environmental disturbances that might affect their quantum states. Some ion trap clocks are so stable that they can detect changes in their tick rates caused by height differences of just a few centimeters. The development of atomic clocks has also enabled new types of fundamental physics experiments. By comparing different types of atomic clocks over extended periods, scientists can search for potential variations in fundamental constants, test alternative theories of gravity, and explore whether the laws of physics might change slowly over cosmic time. These experiments push our understanding of time itself to its limits. Clock networks, consisting of multiple atomic clocks distributed across different locations and connected by high-precision communication links, are becoming increasingly important for both practical applications and scientific research. These networks can detect tiny variations in time's flow across different locations, potentially revealing new information about Earth's gravitational field, the motion of continents, or even the passage of gravitational waves. The precision of modern timekeeping has reached levels where relativistic effects that were once purely theoretical concerns become practical engineering challenges. The design of future spacecraft and space stations must account for the time dilation effects their crews will experience, both for the proper functioning of onboard systems and for maintaining communication with Earth-based control centers. As human activities expand beyond Earth, the challenges of maintaining synchronized timing across the solar system will require new approaches to time distribution and correction. The speed of light creates unavoidable delays in communication between planets, and the varying gravitational fields throughout the solar system create complex patterns of time dilation that must be accounted for in any solar system-wide timing network. These technological developments represent more than just engineering achievements. They provide the tools necessary for exploring some of the deepest questions about the nature of time and space. Each improvement in precision timekeeping opens new possibilities for testing fundamental physics and understanding the universe at the most basic level. Dreams of tomorrow's journeys as we stand at the threshold of a new era in space exploration. The practical implications of time dilation are shifting from theoretical curiosities to engineering realities that will shape humanity's expansion into the cosmos. The missions we're planning today and the technologies we're developing will carry our species into realms where Einstein's insights become lived experiences rather than mathematical abstractions. Consider the current plans for human missions to Mars, representing humanity's next great leap beyond the Earth-Moon system. The journey to Mars involves travel times of 6 to 9 months each way, with spacecraft reaching speeds of up to 40,000 kilometers per hour relative to Earth. While these speeds are still tiny compared to the speed of light, the long duration of interplanetary missions means that even small time dilation effects will accumulate into measurable differences. A crew spending 2.5 years on a Mars mission, including travel time and surface operations, would experience time dilation effects on the order of a few milliseconds. This tiny difference would be completely imperceptible to the astronauts themselves, but it represents the beginning of humanity's direct experience with relativistic effects during long-duration space missions. The precision timing systems aboard such spacecraft would need to account for these effects to maintain accurate navigation and communication with Earth. But Mars missions are just the beginning. As we develop more advanced propulsion technologies, the speeds achievable by human spacecraft will increase dramatically, making time dilation effects progressively more significant. Nuclear pulse propulsion, fusion rockets, or even more exotic propulsion concepts could potentially accelerate spacecraft to significant fractions of light speed, opening the possibility for truly relativistic human travel. Imagine a mission to Proxima Centauri, our nearest stellar neighbor, at about 4.2 light-years distance. With current chemical propulsion technology, such a journey would take tens of thousands of years, clearly impractical for human crews. But advanced propulsion systems might reduce this travel time to decades or even years, achieving speeds where time dilation becomes a significant factor in mission planning. At 10% the speed of light, a spacecraft would experience time dilation with a factor of about 1.005, meaning that every year aboard the ship would correspond to about 1.005 years on Earth. For a 40-year journey to Proxima Centauri, this would result in the crew aging about 2 months less than people who remained on Earth. While still small, this represents a meaningful difference that would affect everything from crew psychology to mission logistics. At higher speeds, time dilation effects become dramatic. A spacecraft traveling at 90% the speed of light would experience time flowing at less than half the rate of Earth-based time. A crew making a 10-year journey to a nearby star system would return to find that more than 20 years had passed on Earth. The society that sent them forth would have continued evolving, developing new technologies, experiencing cultural changes, and perhaps even launching additional missions to the same destination using more advanced spacecraft. This temporal displacement creates profound challenges for interstellar exploration that go far beyond the technical difficulties of achieving such high speeds. Crews embarking on relativistic journeys must accept that they are not just traveling through space, but also traveling into Earth's future, potentially returning to a world that has moved beyond the civilization they knew before departure. The psychological implications are equally profound. Astronauts on relativistic missions would experience normal time flow during their journey, yet they would effectively become time travelers, witnessing the passage of extended periods on Earth compressed into shorter subjective timeframes. Their families and friends would age more rapidly than they do, and the society they return to might be as foreign to them as a different planet. Communication with relativistic spacecraft presents unique challenges. Radio signals travel at light speed, so communication with a spacecraft 10 light-years away requires a 20-year round trip for messages. Combined with time dilation effects, the communication delay becomes even more complex. Messages sent from Earth would arrive at the spacecraft blue-shifted due to the Doppler effect, while messages from the spacecraft would arrive red-shifted and time-dilated. The infrastructure required to support relativistic human travel would need to account for these temporal effects at every level. Mission control systems would need to translate between Earth time and ship time, scheduling operations and monitoring crew health across different temporal reference frames. Medical protocols would need to be adapted for the unique environment of time-dilated space travel, where biological processes occur normally from the crew's perspective, but appear slowed to Earth-based observers. Life support systems aboard relativistic spacecraft would face the interesting challenge of operating in a time-dilated reference frame, while maintaining compatibility with Earth-based standards and expectations. The recycling of air and water, the growing of food, and the maintenance of equipment would all proceed at their normal rates from the crew's perspective. But the consumption of supplies and the wear on systems would appear reduced when viewed from Earth's reference frame. The return to Earth after a long relativistic journey would present unique challenges for both the returning crew and the society welcoming them back. The astronauts would carry with them direct experiences of distant worlds and the unique perspective that comes from having lived through less time than their Earth-bound contemporaries. They would be living bridges between the Earth that sent them forth and the Earth to which they return, carrying knowledge and experiences that span the temporal gap created by their journey. These considerations are already influencing the design of next-generation space missions. While we're still decades away from achieving truly relativistic spacecraft, the principles of time dilation are beginning to inform long-term planning for space exploration. NASA and other space agencies are developing protocols for long-duration missions that account for relativistic effects, and engineers are designing spacecraft systems that can maintain accurate timekeeping in the complex gravitational and velocity environments of interplanetary space. The development of closed-loop life support systems for long-duration space missions provides interesting parallels to time dilation considerations. Just as these systems must recycle air, water, and nutrients within the confined environment of a spacecraft, time dilation effects create a kind of temporal closed loop, where the crew's experience of time becomes partially disconnected from Earth's temporal framework. As we develop artificial intelligence systems to assist with long-duration space missions, these systems will need to be designed to operate across multiple temporal reference frames. An AI system aboard a relativistic spacecraft would need to understand both ship time and Earth time, translating between these temporal frameworks to maintain communication with Earth and properly schedule mission activities. The training of crews for relativistic missions will require preparation for the psychological challenges of temporal displacement, as well as the technical challenges of space travel. Astronauts will need to understand not just how to operate spacecraft systems and conduct scientific experiments, but also how to cope with the knowledge that they are gradually becoming displaced in time relative to the rest of humanity. Perhaps most remarkably, relativistic space travel would make human crews into living experiments in time dilation, providing direct biological and psychological data about how complex living systems respond to extended periods in time-dilated reference frames. While the physical effects of time dilation are well understood theoretically, the psychological and social implications of experiencing time differently than the rest of your species remain largely unexplored territory. As we drift toward the end of our journey through the landscape of time dilation, we find ourselves contemplating questions that stretch beyond physics into the realm of philosophy and human meaning. The reality that time itself can be bent and stretched forces us to reconsider some of our most fundamental assumptions about existence, consciousness, and what it means to experience life in a universe where time is relative. The ancient philosophers who pondered the nature of time could never have imagined that time itself might flow differently for different observers. To them, time was the universal stage upon which all events unfolded, the cosmic metronome that kept identical rhythm for every conscious being in existence. The discovery that time is relative challenges not just our physics, but our most basic intuitions about shared experience and common reality. When we consider consciousness existing within different temporal frameworks, we encounter profound questions about the nature of subjective experience. An astronaut traveling at relativistic speeds experiences thoughts, emotions, memories, and dreams at what feels like a perfectly normal pace. Their internal mental life unfolds with its familiar rhythm. Moments of reflection feel like moments. Periods of concentration feel like their expected duration. And the flow of consciousness maintains its characteristic texture. Yet from Earth's perspective, this rich inner life appears to unfold in slow motion, each thought stretched across extended periods, each emotional response taking longer to develop and resolve. This creates a strange dualism where consciousness exists simultaneously in multiple temporal frameworks, normal and immediate from within, stretched and delayed when viewed from outside. The question arises, which temporal experience is more real? The astronaut's normal subjective experience, or Earth's observation of that experience proceeding slowly? Physics tells us that both perspectives are equally valid, but philosophy struggles with what this means for our understanding of consciousness and shared human experience. Memory presents another fascinating philosophical puzzle in the context of time dilation. The astronauts' memories form at their normal subjective rate, encoding experiences within their personal temporal framework. But these memories represent events that occurred within a time stream flowing differently than Earth's. When the astronaut returns and shares their memories with Earthbound humans, they are literally sharing experiences from a different temporal reality. The stories they tell, the emotions they describe, and the significance they attach to various moments all emerge from a time stream that flowed more slowly than the one experienced by their audience. This creates a unique form of temporal alienation, not just the displacement in time of arriving in Earth's future, but the deeper displacement of having lived through a different experience of time itself. Consider how this affects our understanding of human relationships across relativistic distances. Two people who love each other, separated by relativistic travel, experience the passage of time differently. Their aging occurs at different rates, their memories accumulate at different paces, and their emotional development unfolds according to different temporal rhythms. The connection between them must somehow bridge not just spatial distance, but temporal distance as well. The letters or messages they exchange carry timestamps from different temporal reference frames. A message sent from Earth saying, "I miss you," arrives at the spacecraft carrying a marker from Earth's time stream, but it's received by someone living within a different temporal flow. The emotional content of the message transcends the temporal frameworks, but the context in which it's sent and received involves different experiences of duration and timing. This temporal separation creates new forms of longing and connection that human beings have never experienced before. The astronaut knows that while they experience days and weeks of travel, their loved ones on Earth are experiencing slightly longer periods of separation. Time itself becomes a participant in their relationship, creating a subtle but persistent asymmetry in their shared experience. The concept of simultaneity, the idea that events can happen at the same time, loses its absolute meaning in a relativistic universe. An astronaut and their Earthbound friend can no longer point to any moment and say definitively that they are experiencing now together. The present moment becomes relative, dependent on reference frame, creating a philosophical puzzle about shared existence and common experience. Yet perhaps there's something beautiful in this relativistic understanding of time and consciousness. Rather than diminishing human connection, time dilation reveals new dimensions of what it means to be conscious beings in a vast and complex universe. The astronaut and their Earthbound friend may experience time differently, but they share something more fundamental: the capacity for thought, emotion, and memory that transcends any particular temporal framework. Their consciousness, while embedded in different time streams, participates in the same fundamental mystery of awareness and experience. Whether thoughts unfold quickly or slowly, whether memories form rapidly or gradually, the essential nature of consciousness, its capacity to experience, to reflect, to love, remains unchanged across relativistic effects. This suggests that while time dilation affects the rate at which conscious experience unfolds, it doesn't alter the fundamental nature of consciousness itself. The astronaut remains fully human, fully conscious, fully capable of wonder, love, and understanding. Their humanity isn't diluted by traveling through spacetime at high speeds. It's simply expressed within a different temporal context. The philosophical implications extend to questions about personal identity and continuity of self across time. If you traveled on a relativistic journey and returned to Earth having aged less than your earthbound friends, would you still be the same person? Your memories would span a shorter subjective time frame. Your body would show less wear from the passage of time, and your psychological development would have occurred at a different pace. Yet the core of who you are, your values, your personality, your way of understanding the world, would have developed normally within your own temporal reference frame. You would be authentically yourself, shaped by genuine experiences and real growth, even though that development occurred within a time stream flowing differently than Earth's. This connects to broader questions about how we understand human life and meaning in a universe where time itself is relative. If time can stretch and compress, what does this mean for concepts like urgency, patience, and the preciousness of moments? Does a beautiful sunset, experienced within a time-dilated reference frame, carry the same emotional weight as one experienced in Earth's time stream? The answer seems to be that the subjective experience of beauty, meaning, and significance remains fully intact regardless of the temporal framework within which it occurs. The astronaut watching an alien sunrise from the surface of a distant world experiences genuine wonder and joy, even though that experience unfolds within a time stream flowing differently than Earth's. The meaning they derive from that moment is authentic and complete, undiminished by relativistic effects. This suggests that human meaning and value aren't dependent on any particular rate of temporal flow, but rather on the capacity for consciousness to recognize beauty, significance, and connection, regardless of the temporal context in which it finds itself. Love doesn't become less meaningful when experienced in a time-dilated reference frame. Beauty doesn't lose its power to move us, and the search for understanding and connection remains as compelling as ever. Perhaps most remarkably, time dilation reveals that consciousness itself transcends the particular temporal frameworks within which it operates. While the rate at which conscious experience unfolds may vary, the essential nature of consciousness, its ability to experience, reflect, love, and find meaning, remains constant across all reference frames. This points toward something profound about the relationship between consciousness and time. Rather than being prisoners of time's flow, conscious beings are in some sense independent of the particular temporal rhythms within which they find themselves. Consciousness adapts to whatever temporal framework it inhabits, maintaining its essential character while remaining flexible enough to operate within different time streams. The astronaut returns from their relativistic journey not diminished by their temporal displacement, but enriched by having experienced consciousness within a different temporal context. They carry within their memories the unique perspective that comes from having lived through time's flexibility, having experienced firsthand that reality is far stranger and more wonderful than our everyday experience suggests. As our exploration of time dilation draws to a gentle close, we find ourselves floating in a space of wonder, contemplating the profound beauty of a universe where time itself can bend and stretch like a cosmic river, responding to the presence of matter and motion. The astronauts we've imagined, racing through the cosmos at tremendous speeds, carry within their journey something miraculous: the lived experience of time's flexibility, the embodied knowledge that reality is far more mysterious and beautiful than our everyday experience reveals. Think of them now, these travelers through spacetime, as they make their way back toward Earth carrying memories from distant stars. Their ship glides through the cosmic dark, its hull warm with recycled air and gentle with the hum of life support systems. Inside, the crew moves through their daily routines, sharing meals, tending to scientific instruments, gazing out at the slowly changing constellations, all unaware that each moment of their experience unfolds within a time stream flowing, just slightly more slowly than the one carrying Earth through its own journey around the sun. They are living poetry, these astronauts, their very existence a testament to the deep connections between space, time, matter, and consciousness. Every breath they take, every thought they think, every moment of wonder they experience occurs within Einstein's gentle equations made real. They have become time travelers not through exotic machinery or impossible technologies, but simply by moving very fast through the universe that surrounds us all. When they finally return to Earth, stepping once again onto solid ground under familiar skies, they will carry within their bodies and minds something unprecedented in human experience: the direct, lived knowledge of time's relativity. They will have aged slightly less than their earthbound friends and family, not through any medical intervention or life extension technology, but through the simple fact of having traveled at high speeds through spacetime itself. Their homecoming will be both joyful and bittersweet, marked by the strange reality that they have become visitors from a slightly different temporal realm. The world they return to will have moved just a little further into the future than their own experience would suggest, creating a subtle but real displacement that connects them to the deepest mysteries of space and time. Yet in their eyes, we might see not alienation, but wonder, the profound satisfaction that comes from having experienced reality at its most fundamental level, from having lived within the equations that describe how the universe actually works rather than how our everyday experience suggests it should work. They have danced with time itself, partners in the cosmic choreography that connects all matter, energy, space, and time into a single, magnificent whole. The children who grow up in a world where such journeys are possible will inhabit a different relationship with time than any humans before them. They will know from childhood that time is not the rigid, universal constant their ancestors imagined, but a flexible, responsive aspect of reality that bends to motion and mass. This knowledge will shape their understanding of existence itself, creating new forms of poetry, new philosophical insights, and new ways of understanding what it means to be conscious beings in a relativistic universe. As we ourselves drift toward sleep, let us carry with us this sense of wonder at time's flexibility. Every moment we experience, every thought we think, every breath we take occurs within the gentle curvature of spacetime created by Earth's mass and our motion through the cosmos. We are all, in our own small way, time travelers, following our planet's path through spacetime at speeds that create tiny but real-time dilation effects. The GPS satellites passing overhead experience time differently than we do. The International Space Station, visible sometimes as a bright point of light moving across the evening sky, carries astronauts through a slightly different temporal framework than the one we inhabit here on Earth's surface. Even the atoms in our bodies, when they absorb and emit light, participate in the quantum mechanical processes that define time itself at the most fundamental level. This is the universe Einstein revealed to us, not a clockwork mechanism ticking away with perfect regularity, but a dynamic, responsive, living fabric of space and time that dances to the rhythm of matter and energy. We are not separate from this cosmic dance, but participants in it. Our consciousness embedded within the very spacetime, whose curvature creates the gravitational field that holds us to Earth's surface. The time dilation experienced by astronauts serves as a gentle reminder of our deep connection to the cosmos and the fundamental principles that govern reality at every scale. From the smallest quantum fluctuations to the largest structures in the universe, time responds to the presence of matter and energy, creating a rich tapestry of temporal experience that encompasses everything from our own quiet moments of reflection to the extreme time dilation near black holes billions of light years away. As you close your eyes and feel yourself settling into sleep, imagine yourself floating gently through spacetime itself, carried along by Earth's motion around the sun, the solar system's journey around the galactic center, and the galaxy's movement through the expanding universe. You are a traveler through time and space, experiencing each moment within the grand cosmic context that Einstein's insights revealed. Let your thoughts drift like those astronauts returning from distant stars, carrying within your mind the wonder of a universe where time itself can stretch and bend, where consciousness can experience reality from different temporal perspectives, and where the simple act of moving very fast through space can become a form of time travel as beautiful and profound as any story ever imagined. Sleep well, fellow traveler through spacetime, knowing that your dreams unfold within the same magnificent cosmic dance that carries astronauts through their relativistic journeys among the stars. Time flows gently around you, responsive to your motion, influenced by Earth's gravity, connected to the deepest structures of reality itself. In your rest, you participate in the cosmic rhythm that connects all things, all moments, all possibilities within the endless, wonderful flexibility of time itself. Sweet dreams among the gentle currents of spacetime, where every moment is a small miracle of consciousness, experiencing the universe from within, and where time itself reveals its secret nature as not a rigid ruler, but a responsive partner in the cosmic dance that connects us all to the stars, the galaxies, and the infinite mystery of existence itself. Again, this is Luna. Don't forget to hit like and subscribe so we can explore again together. See you in the next one.